Hi everybody. What we're going to do in this video is follow along this note sheet. So if you don't have this printed out, you can find it on Moodle. And we're going to talk a little bit more in depth about how we can do control mass analysis, which is going to be similar but a little bit different to how we've been doing control volumes. So before we start, we're going to talk about the difference between point functions and path functions. These are both things that we've encountered before, but we haven't really used this specific terminology to be able to name them. So a point function, that is a function whose value depends only on the state. Maybe another way to think about this has a definite value. At a state. Okay, more clear with examples. So this would be something in this class like density, where if you know, say, temperature and pressure and what specific fluid it is, you would know what the density is, and two things with the same temperature, pressure, made of the same material are going to have the same density. This would be also something like temperature, pressure. Neither of these depend on the history. You just need to know what they are, and it's the same. Also something like enthalpy, entropy, internal energy, specific volume, things that we can look up in our tables. The reason we can look them up is because they are point functions. We can look up their value when they go together at a specific state. This would also be something like kinetic energy and potential energy, where, for example, if we know the mass and the height, we know the potential energy, and that is kind of clearly defined at that given state. Okay, this is in contrast to path functions, where these are functions where the value depends on the pathway or process between initial and final states. So again, in thermo, these would be heat or Q and work. So heat and work are really fundamentally different types of things than, say, temperature and pressure. And we've run into that. We haven't been able to look up heat in, say, steam tables. We've been able to look up temperatures and pressures and enthalpies in steam tables. We've always had to calculate things like heat and work from energy balances, from things that we know about the process, whether it's, a 70% efficient turbine or really what have you. So it depends on what's actually happening in the system. Maybe something we haven't explained explicitly is we've always put these two on different sides of our energy balance equation. So we've had equations that look something like this. This is going to be our equation for control masses, where there's deltas on one side and then Q and W on the other side. Our energy balance for control masses is going to be a little bit simpler, at least in how we typically write it. Typically, we would have kinetic energy, potential energy. We're just going to neglect those kind of right off the bat, because very often we're not analyzing systems where our control mass is moving from one place to another. So we're going to be looking at things like pistons and cylinders, and we're not going to be throwing them across the room, so they're not going to have changes in kinetic energy and potential energy. It's not always the case in fluids. For some of you that will take that maybe next semester or next year, you will see systems where we're looking at an individual particle of fluid and it is moving from one place to another. But typically in thermo here, we won't. We also have a delta U rather than delta H on that left side. But recall H and U are friends. They're actually really closely related. The difference between the two is this PV term, which this is, if you remember, this is flow work. So this is a term that always came up when we had stuff moving in and out, like an inlet and an outlet type term, which we do have all the time for control volumes, and we don't have for control masses. So that's why instead of H, we just have U, which is the internal energy, or really the thermal energy. The thermal energy of matter. All right. So just a quick summary. Often we'll use terminology like this, W12, to say this is the specific path between, say, point 1 and point 2. We'll do that instead of saying this is the work of turbine 1 or compressor 2 or whatever else we would have done in control volume problems. We'll look at the between state 1 and state 2. Because internal energy is a point function, we'll deal with things like delta U. That's going to be the same regardless of path. And heat transfer, that's another path function, so we'll use this same kind of goofy subscript terminology where we'll look at the difference between, say, state 1 as an initial state and state 2 as a final state. So let's look in an example problem how this stuff actually works out. Okay, so here's a simple practice problem. Some of the things are already drawn here for you if you printed this out from Moodle. But basically what we're going to do is we're going to look at a piston cylinder arrangement. So this is what's kind of crudely drawn down here. And we're looking at it at 3 different steps, but it goes from an initial state where we know temperature and pressure. That's state 1. We go from that state, we expand to a final volume. That's twice the initial volume, and a final pressure of 400 kPa. So that's the final state, which is this guy over here on the far right, 3. We're going to do that in a couple different ways. Along each of these different pathways between state 1 and state 3, we're going to look at different pathways and how that influences work. This should be different in each path because work is a path function, where something like delta U should stay the same. Okay, we're going to look the first path. We're going to look at a constant pressure heating, then a constant volume heating. So we're going to first look at this part between 1 and 2, where we're staying at 300 kPa, but we're heating it up. That's expanding it until we say hit a stop. Then we're going to continue to heat at constant volume until we get to our final pressure of 400 kPa. All right, so those are going to be our 2 steps, or that's going to be our pathway for this first attempt at solving it. There are going to be a couple key equations. I'm going to put them in kind of a cloud of importance over here. These are going to be equations that will come up. They should look sort of familiar. These are equations for reversible work and reversible heat transfer. The reversible work one up at the top should look familiar, but it's not actually quite the same as what we ran into in control volume problems. If you remember right, we had work equals negative VdP. So a little bit of a change. We'll discuss why that is, but the one for heat, Q, that one actually is the same as what we saw for finding Q for reversible processes in control volume systems. So that one hasn't changed. All right. So how do we go about this? Well, it's going to be really similar to problems that we've solved before. So we know pressure and temperature. Once we know 2 things, we can look up the others. So we can look up, say in Cat 3, what the internal energy is, 2729 kilojoules per kilogram. If we're looking that up in either Cat 3 or our steam tables, it's just right next door to H. We can also look up our volume, 0.7964 meters cubed per kilogram. We know our pressure has not changed between state 1 and state 2. That's what we're given in our problem statement. We know the volume has doubled, so we know what that is. That's 1.593 meters cubed per kilogram. Once we know two things, we can look up everything else. So this U2, the internal energy at state 2, is just looked up, say by either steam tables or Cat3, as 3594 kilojoules per kilogram. Our volume isn't changing between step 3 and state 2 and state 3. So that's 1.593 meters cubed per kilogram still. Our pressure has gone up from 300 to 400. So now our internal energy, if we look that up, is 4273 kilojoules per kilogram. All right, now we want to find work. So to find work, we're going to use this equation here to find the total amount of work. For control mass problems, we're not going to have W dot. We're going to have just capital W, a total amount, because we don't have a rate. We just have a total mass. We don't have a mass flow rate. So we have M up here rather than, say, M dot. Kilograms rather than kilograms per second. So we should get work in kilojoules rather than kilojoules per second, which is kilowatts. So we'll look at how that works. We're trying to solve that integral. So this integral here. Luckily for this particular process, this is a pretty easy one. So we're trying to solve this from 1 to 2. Pressure is constant. So pressure can come out of the integral, and we're then simply solving the integral of dV, or d volume, which is just delta volume. So this is mass times pressure times delta volume when we solve that integral for constant pressure. We can put some numbers to this. 0.1 kilograms, 300 kPa, and our change in volume, final minus initial, 1.593 minus 0.7964 meters cubed per kilogram. We might need to look up how to do the units on this, but I remember that a kilopascal is a kilojoule per meter cubed. Again, you might need to look that up. You probably do. But we can then do this math and find that this is 23.89 kilojoules. So that would be the work between what we're calling state 1 and state 2. That's why we have those little subscripts. We can now find the work between state 2 and 3. I'm going to do that on the next page. Right, for state 2 and 3, we don't have a change in volume. So what we can say is that this integral, again, becomes very easy to solve, even easier than it was before, because if dV is 0, because there's no change in volume, then work is 0. So like we had in control volume problems, when we looked at problems like that, we needed a spinning, moving mechanical part to be able to have work in the system. So something like a nozzle, work was 0 because there weren't moving parts. Or something like a pump, work was non-zero because we had moving parts. In a control mass problem, we need not moving parts, we need a moving something. So we need a moving boundary or a volume change to be able to actually take work out or put work in. So we could say here that the total work, W between 1 to 3, is what W W12 plus W23. W23 is 0, so this is just 23.89 kilojoules. We can draw a diagram of this process. I already have it sort of sketched out here. We have our initial state and final state. Our first step is a constant pressure expansion. So we're going up at constant pressure here to 2. Then from 2 to 3, we're going from 300 kPa up to 400 kPa, but not seeing a change in volume. If we wanted to shade in the work is the area here under this curve. So we can see that straight vertical line between 2 and 3, because it's a vertical line, it doesn't have any area under the curve, and that's why the work is 0. If we want to convince ourselves the work, for the other one, if we just found the area of that shape, it would exactly match the equation that we got for work 1-2. We're going to continue this with a few more practice problems on the next page, but we'll stop this video and pick that up in video part 2.